What's up, guys? It's Mr. Bringle, and today we're going to talk about acceleration. So, to get us started here, what is acceleration? So, acceleration is literally defined as the rate of change of velocity of an object. And so, all that has to be present for an object to accelerate is a change in velocity. That could be up or down. And velocity includes direction, so it also includes a change of direction. Okay, so the misconception, the most common misconception with acceleration is that if somebody says, oh, that thing's accelerating, we assume it's speeding up. But by definition, acceleration simply means change in velocity over some period of time. So this could mean speeding up or slowing down, which I would say is something that you should probably highlight in your notes. Now, acceleration is measured in meters per second squared. So that would be this. This would be the symbol right here that we use for acceleration unit of measurement. And if you think about it, the equation down here, we have velocity divided by time, and the unit of measurement for velocity would be a meter per second, and the unit for time is second, so a meter per second, or a meter per second squared. Now, what does that really mean? Like, what is a meter per second squared? So, if I told you that an object was speeding up or slowing down at 10 meters per second squared, that means it's changing its velocity by 10 meters per second each second. So if it's speeding up, it's increasing its velocity by 10 meters per second every second. And if it was slowing down, it would be losing 10 meter per second velocity each second. Okay, so that basically means if it started from 0 meters per second, after 1 second, it would be moving 10 meters per second. And if we wait 1 second longer, it should have increased by another 10 meters per second to 20 meters per second at that point. Moving on, let's look at a quick example here. A Ferrari goes from 20 to 60 meters per second in 4 seconds. What is the acceleration of the Ferrari? So I always want you guys to be in a habit of underlining things that we've been given: 20 meters per second, 60 meters per second, 4 seconds, and then it says, what is the acceleration of the Ferrari? I like to circle what we're solving for. So if it goes from 20 meters per second to 60 meters per second, that means this is my initial velocity, this is my final velocity, and then it gives us the time right here, and acceleration would be the letter A. So we do want to, I always like you guys to write out your knowns and unknowns over here, even though it's somewhat redundant based on what we just did. We're going to go ahead and do it. The initial velocity is 20 meters per second. The final velocity is 60 meters per second. And the time, 4 seconds. Acceleration is our unknown. We're going to use that equation from the last slide. Acceleration is equal to change in velocity over change in time, or in this case, when we're dealing with an initial time of 0 seconds, the change in time is just the time it takes. So in this case, 4 seconds. Now, this equation can also be written like this. We can change in velocity would be the final velocity of the object minus the initial velocity, and then we would divide that by the time interval. So as we actually solve here, we are going to plug in the final velocity first. Don't mix that up. Don't write the initial velocity. So this is going to be 60 meters per second minus 20 meters per second divided by the time interval of 4 seconds. So we can see here that 60 minus 20 is going to be 40 meters per second, and that's going to be divided by 4 seconds, and we will find that our acceleration is equal to a positive 10 meters per second squared. And we do need that positive sign on there to indicate direction. Acceleration has direction because we use velocity to calculate it, and velocity has direction. So we have to indicate direction with a cardinal direction, north, east, southwest, something like that, or right, left, up, down, forward, backward, or we can, in physics, use positive and negative symbols. If the object's moving in the positive direction, positive, and if it's moving in the negative direction, negative. Let's go ahead and move on. So to elaborate on this, acceleration does have direction, very key. And acceleration is a vector quantity. So vectors have both magnitude and direction. Magnitude is how much. So when you have something like 5 meters per second north, the number 5 tells you how much. That would be the magnitude. And then the direction would be north in that situation. As I mentioned before, we can use positive and negative symbols to indicate direction in physics, and we do that quite often. Direction is relative in physics. You know, for me, I don't know what shows up on the video, but this is my right hand, right? This is to the right, this is to the left. But if I just turn around, now the right side is the other way, right? So direction's all relative in physics. We pick a direction as positive, pick a direction as negative, and then we leave it the same throughout the whole experiment. So the main thing here is there's two very simple rules to follow here. It's kind of one rule, but for two different situations. If the object is speeding up, the direction of the acceleration must be in the same direction as the velocity, which is the direction the object's moving. So if I'm moving north and speeding up, the direction of my acceleration is also north. Think about it like it's adding to it, right? It's speeding the object up. The acceleration must be in the same direction that the object is moving. Now, on the flip side here, if an object is slowing down, the acceleration direction will always be opposite the direction of the velocity or direction of movement. And again, think about that. If I'm moving north and I want to slow down, I need an acceleration in the opposite direction. I need an acceleration to the south so that I'm losing velocity instead of gaining it. Now, we do a lot of work with position and velocity versus time graphs. Sorry, I was trying to move my video here out of the corner, but I will move that when I need to. So at this point, we know that the slope of a position versus time graph tells us the velocity of an object. So slope of position versus time tells us velocity. So that's really important because in our previous unit, we only ever had constant slopes. Something like, for instance, this right here. This would be a constant slope. The incline of this line is not changing. It is going from the bottom towards the bottom of the graph towards the top, but that doesn't mean that the slope is changing. The slope is constant. It would only be a changing slope if it changed angles, right? So this means constant. Apologies. Let me get this means constant velocity here when we have that slope that is constant. Now, that means that if the slope changes, then our velocity changes, and that is the definition of acceleration. So when we come over to this graph, I could show you a number of different things, but let me just show this right here. This is basically a curved line where the slope is always changing. So I tried to do a curved line that has a more or less constant acceleration, but kind of hard to do by hand. So just imagine that that's a nice smooth curve, and that shows us, if you look at the slope down here, it's pretty flat down here. So that would be a very low velocity, very small velocity, and then it's steep up here, right? So the incline has changed. It wasn't constant like it was over here where that slope doesn't change from the beginning to middle to end, but over here it's like flat, and then it's kind of diagonal, and then it's really steep up here. So the slope changes, therefore the velocity changes, and by definition, that is acceleration. Okay, so now on a position versus time graph, there's basically two graphs that will indicate an object that is speeding up. And you know that the object is speeding up because the slope gets steeper over time. So I just showed you one of those. It looks like this, right? Or something more. We'll try to do a little bit better there. That's better, right? This is getting steeper, so this is flat right here. And then this is steeper up here. We could also show this moving in the negative direction. So if you think about it, like this is the positive direction, this would be 0 meters because this is our position over here, right? So 0 meters, positive direction would be moving this way. So that means that if we start at a positive position and move backwards, we would show that the object starts up on the y-axis pretty high, and then we'll move down to the lower portion of the graph. So what that would look like would be something like this. We start with a flat slope, and then that slope just gets steeper, 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 steeper over time, right? So this up here is flat, and this down here is steep. So we always go left to right on the graph, and if that slope gets steeper, whether it's going up or down, it doesn't matter. If it's getting steeper, that means that it's getting faster because the slope tells us the velocity of the object. So we can then show an object that is slowing down by doing the opposite. We show that the slope gets less steep over time, or it gets flatter over time. So maybe it starts really steep like this, and then over time it just kind of levels out. This would be steep down here, and this would be flat up here. So we're going from a very high velocity in this area to a very low velocity in this area. And again, that's moving in the positive direction. We can also show this moving in the negative direction, which means we would start with our line up here and we would want it to be steep, and then it needs to get flat over time, so it would look something like this. Okay, so again, steep at the start on the left side of the graph, and it is flat at the end on the right side of the graph. So this object would be slowing down. Okay, so velocity versus time graphs now. In our speed and velocity unit, we only dealt with constant velocity. And so what shows us constant velocity would be, first, remember that we have the velocity is on our y-axis now. This really matters because that means the slope of the line does not tell us the speed anymore. The speed or the velocity of the object is its vertical position on this graph. You can have a positive velocity, you can have a negative velocity. It depends on which direction you're moving. So if there is a horizontal or flat line, that indicates that your velocity is not changing. So if I wanted to show a constant velocity, I could show a positive velocity like this. That would be constant. I could also show a negative velocity like this, right? Either of these would be constant velocities because the slope doesn't change. If you think about numbers that might be on this axis over here, we've got this, we got this. These numbers here, let's just pretend that that's 3 meters per second. This would be like -1, -2, and -3 right here. So this would be positive 3 meters per second in red, and that would be a constant number because it doesn't change, right? It doesn't go down to 2, it doesn't go up to 4, it stays right at 3. This is at 3 meters per second negative, so this would be same speed, different direction. So if we want to show that an object is accelerating, then what we have to do is we got to change the slope of the line. It can't be a flat line. It's got to cover multiple numbers on the y-axis. So whether it's going up or down doesn't matter. As long as it's changing its velocity, it would be accelerating. So I could do something like this, where the object starts at 0 meters per second here, and then it goes up to a positive velocity. We could also show that it starts at a positive velocity and it goes down to 0 meters per second. So basically a diagonal line of any type will show a changing velocity on this graph, and that indicates the object is accelerating. Okay. And we're only ever going to look at examples of constant acceleration. So notice that this slope right here is a constant slope, right? This is constant slope, and the slope of a velocity versus time graph tells us the acceleration of the object. So the slope always tells us something, right? The slope of a position versus time tells us velocity. The slope of a velocity versus time tells us acceleration. So we can always look at that to help us out. Moving along here. So looking at a velocity versus time graph that shows an object that's speeding up, basically the main thing is that 0 meters per second is right here, right? That is 0 meters per second. So for an object to speed up, it certainly can't be moving towards 0 meters per second on the graph. It must go away from it. So to do that, there's essentially two options. We can show the line looking like this, where it starts at 0 meters per second or somewhere near 0, and it goes to a non-zero value on the positive side of the graph. You could also do the same thing, but on the negative side of the graph, we could start at 0 meters per second and we can move away from that. Now, this can sometimes get confusing because we have two different slopes here. We have a positive slope and we have a negative slope. And so often people will look at the negative slope and they say, oh, well, that object's got to be slowing down because the line is going down. Don't ever think about it like that. You have to look at where the line starts and where it ends. Think the song Cotton Eye Joe, right? Where did it come from? Where did it go? So it came from 0 meters per second or a low velocity and it went to a non-zero value. Got to be speeding up. Now, flip that for slowing down, and we want to be moving towards 0 meters per second. So this line right here, the x-axis, is 0 meters per second. So two ways to show this. We start on the top half of the graph, and we move down towards 0 meters per second. That is one option, right? So we end at 0. We started at a non-zero value. We went down to 0 on this. So this would be slowing down in the positive direction. And then we can also show slowing down in the negative direction, which would, again, look a little funny because it's got a positive slope here. But remember, the slope tells us the direction of the acceleration, whether it's positive or negative. It does not tell us if it's speeding up or slowing down. Okay, the velocity is on this graph. You need to look at where the velocity came from and where it went, right? So in this scenario here, we have the object starting at a very negative number. So just think about it like, let's say that this is -5 meters per second. And then at this point right here, that's 0 meters per second. So even though it has a positive slope, it ended at 0 meters per second, meaning that it had to be slowing down. All right, the last thing here are some equations for acceleration. And these are equations that we'll use throughout the unit. I just want them on here so that you have access to them. You can check them out. You might just make some notes that V stands for velocity, A stands for acceleration, T stands for time, and then delta X, as we learned in our previous unit, stands for the displacement or change in position of an object. The letter G down here, G is a constant. That is the acceleration that's caused by the force of gravity. That will be relevant whenever something is accelerating because gravity is pushing on it. And then we do have an equation over here for the area of a triangle, which will be used later on. We'll talk about that when we need to. All right, that concludes our notes on acceleration. Make it a great one.